We can measure the biological benefits of a night's sleep with high precision. It triages memories, clears metabolic waste, and maintains synaptic homeostasis. It is a vital period of physiological repair. However, these functions don't explain why the brain requires such a rigid, repeating architecture. If sleep were only about biological maintenance, a continuous resting state would suffice. Instead, the human brain cycles relentlessly between the high-amplitude waves of NREM and the rapid-fire activity of REM. The Brain Kinematics Model suggests this cycle is a mechanical requirement of hierarchical regulation. Under this framework, the peaks and valleys of a sleep graph reflect alternating phases of network contraction and expansion. This oscillation manages a single critical variable, residual organizational strain. Every experience leaves behind partially resolved changes in neural connectivity. This strain builds up during waking hours and must be systematically reduced to maintain the network's integrity. The cyclical architecture of sleep exists to resolve these structural mismatches. It is the brain's method of stepping total network strain down through iterative loops. Neural memory operates as a semi-fractal hierarchy. Modifying one node sends changes rippling outward. Waking cognition constantly bombards this tree. While local nodes adapt, deeper branches fail to align, creating pockets of tension. This tension is residual strain, a physical mismatch locked across the network. Resolving this scattered strain requires the brain to map and adjust connections across the entire hierarchy. This process is too computationally intensive to occur during active sensory processing without causing massive interference. The system requires a complete withdrawal from external inputs to begin the mechanical work of reorganizing the strained hierarchy. This period of reorganization begins with deep NREM sleep, which functions as the network's zoom-in regime. The high-amplitude, low-frequency EEG waves seen in deep sleep indicate a state of massive organizational coherence. These waves force large populations of nearby neurons to oscillate in unison. This localized synchronization creates a stable environment where specific neural assemblies can participate in common strain fields. This phase drives synaptic plasticity at the local level. It refines and stabilizes specific memory motifs, physically reinforcing the individual threads of the day's experience. Deep NREM serves as a reinforcement algorithm. It successfully repairs the local branches, though it leaves the system momentarily disconnected from the wider network. To complete the repair, the brain must move from local refinement to global integration. This is the zoom-out regime of REM sleep. During REM, high-frequency activity returns, signaling a shift toward organizational fluidity. The network can now redistribute the localized modifications made during NREM across the broader semi-fractal structure. NREM2 acts as the coupling bridge for this transition, gradually opening local modifications to their neighboring organizational structures. Global redistribution is not a perfect process. When new data is integrated into the macrostructure, it inevitably creates new misalignments in distant branches of the network. This creates a new set of local mismatches, which in turn require another NREM phase to resolve. The sleep cycle repeats as an iterative optimization loop. Each oscillation progressively steps down the network's total strain until a global equilibrium is reached. We can observe this mechanical indexing in dream logs. In one case, a dreamer is stopped at a gate and asked for an ID. After a frantic search through a purse, they find the ID hidden inside a folded piece of paper and pass through. The dream begins with a demand, the gate, which the brain processes as a specific packet of organizational strain. The search through the purse reflects the network's attempt to activate various candidate pathways to resolve that strain. Finding the ID in a folded paper represents the discovery of a specific associative bridge. It links disparate branches of the memory hierarchy, allowing the data to finally snap into place. This is the mechanism behind dream condensation. The brain is compressing extensive memory organizations into higher-order motifs, seeking the most efficient structural path. When the network finally settles into a stable, balanced configuration, we experience that moment of equilibrium as a symbolic image. The symbol is the conscious readout of a solved organizational problem. Dreams provide a window into a system in the process of mechanically balancing itself. This mechanical perspective suggests that sleep is not a biological accident, but a functional necessity for complex integration. Any system that integrates data from subordinate units, whether that system is a biological brain, a massive social network, or a sophisticated artificial intelligence, functions as an integration center. In any system where higher layers must organize continuous lower-level inputs, residual strain is an inevitable byproduct of operation. If the system is to remain stable over time, that strain must be addressed. As the complexity of the hierarchy grows, the need for periodic internal reorganization becomes more acute. The system must eventually halt its external interactions to execute the structural repairs required to maintain its equilibrium. From this viewpoint, biological sleep stands as one specific evolutionary solution to a problem faced by any complex integrating system. It is a fundamental requirement for the long-term stability of an organized mind.